Hello everyone, welcome to Lab 2 of Analog Electronics. This lab has to do with MOSFET characterization, and it's called that because we're going to extract some of the long channel modeling parameters of MOSFET transistors. MOSFETs play an important role in analog electronics, so it's important that we understand them before we actually get to the labs that we use them to build circuits. A lot of students struggle with this pre-lab because it's more theoretical instead of long, tedious hand calculations. And so we're not looking to measure voltages or currents or to calculate voltages and currents. We're just trying to show basic understanding of how a MOSFET works. So the first part of the pre-lab asks us to determine whether the MOSFET's circuits in parts 1 and 2 will be in triode region or linear or in saturation region. So I've drawn that circuit here already. In this lab we're going to be varying the drain voltage and the body voltage as I've shown here. And this transistor is diode connected as shown. Diode connected means the gate and the drain are at the same potential at all times. They're hardwired together. And so we call that a diode connected connection. So if we consider what the threshold is for saturation, the requirement is VDS has to be greater than VGS minus VT. And this term is sometimes called VDS sat or overdrive, depending on what book you look at, VGS minus VT. So if we look at this circuit, VDS happens to be the same value as VGS because we've tied the gate and the drain together. So VGS is equal to VDS for this specific circuit, diode connected circuit. So if we go back to that equation and just substitute for one of them, VGS has got to be greater than VGS minus VT. Subtract VGS from both sides, you have 0 greater than minus VT. Now VT is a positive quantity, so 0 minus, 0 is always going to be greater than minus a positive number. So this is always true. And therefore, we are in saturation. And you can do the same analysis for the PMOS. If you want to use the reverse notation, it's going to be VSD is greater than VSG minus VT. And you can go through the same analysis and get the same result. Or you can just put absolute value around all the parameters and you get the exact same equation. And because it's diode connected, it's always in saturation. The next part of the pre-lab, let's see, consider the mathematical model of the IV characteristics of the MOSFET and qualitatively sketch the expected appearance of the plots in part 5. How are the slopes of these plots related to the transconductance parameters? How would you find the threshold voltages of these plots? So let's look at part 5 and see what it's plotting exactly. Part 5 wants the plot of square root of ID versus VGS. Equal to VDS, because it's diode connected, this data. So let's consider the saturation current equation. ID is equal to 1/2 K prime W over L VGS minus VT squared. And don't worry about the channel length modulation addition. We'll just focus on this. If we need to plot square root of ID versus VGS, let's take the square root of this equation on both sides. Square root of ID is equal square root 1/2 k prime w over L BGS minus VT. The square goes away because we took the square root. And we can distribute that to both the parameters and the parentheses. So we're left with square root of ID is equal to 1/2 k prime w over L VGS minus square root 1/2 k prime w over L VT. And we're trying to plot ID versus VGS. And if you look at this for a few seconds here, you'll realize that this is a straight line. This is a linear equation where this is y, this is your slope, this is x, and this is b, the y-intercept. Y equals mx plus b. So if we were to plot this, I think I got room over here. Plotting square root of ID versus VGS. We expect this to be a straight line. The y-intercept is going to be a negative value because VT is positive, square root of this stuff is going to be positive. So this is actually going to intercept down here somewhere, if you could do that. But if you did a straight line upwards from there with a positive slope, then we expect a straight line like that with our data. And from this, we are able to determine VT and K prime. So if we have multiple data points, which we're going to do in the lab, we'll have multiple data points here. We can get a best fit line and have it y equal to mx plus b is what Excel or MATLAB or whatever tool you use, that's what that'll spit out. You can use this equation that it gives you, map it back to this equation here, and you can figure out what VT is and K prime. For example, this tells us that the slope is equal to 1/2 K prime W over L. And W over L is given in the data sheet. I think it's 100, but just double check that. And so if you know the slope from the data, you can square the slope, multiply by 2, divide by W over L to figure out what K prime is. Or you could figure out K is equal to K prime W over L. If you don't want to look up what W over L are, you can just figure out what K is. And once you know what K prime is, or K, you can use the B parameter, the y-intercept, and you can use that to solve for VT. Something to note from this equation, if y equals 0, you can take out this square root of 1/2 K prime W over L from both of those parameters, and at that instance VGS is equal to VT. So actually the x-intercept here lines up with the threshold voltage. So you could get it from that as well. So that's it for part 2. The next, let me scroll back up and look at the next part of the Prelab. Part C is asking to sketch the appearance of plots in part 6. How are the slopes of these plots related to the body effect parameter? All right, body effect parameter. move this up. So body effect, if you remember from class, changes the threshold voltage. And it does so according to this equation. It should look familiar maybe, if you look back in your notes or at the text. And so with this part of the lab, we're trying to figure out what is gamma. We're trying to figure that out from data. And so we're going to plot VT versus all this stuff in parentheses here. Now if we consider this another straight line equation, we have y equal to mx, and VTO is the b term here. So x is what we're going to plot against. We want to plot VT versus 2 phi plus VSB minus square root of 2 phi. And so that's how that gets mapped to the best fit line. So if we construct a similar plot like we did before, and we want to plot threshold voltage versus square root of 2 phi plus VSB minus square root of 2 phi. And we're only going to get 3 data points for this based on the data that the lab has you collect. And we know that gamma should be positive, so the slope's going to be positive. We're only going to deal with positive values of VSB, and so we're going to stay in the right hand part of the axes here. And our offset's going to be VTO, which is a positive quantity as well. So we'll have 3 data points like this, positive slope. If you connect those 3 things together, those 3 points, the y-intercept here corresponds to B, which is VTO. So you can get VTO from that, along with the slope here corresponds to gamma, like so. And so we get y equals mx plus b from the best fit line in Excel or MATLAB or whatever tool you use, and you can map m to gamma and b to VTO, and that's how you can figure out the body effect coefficient, gamma. This kind of goes hand in hand with the previous plot, because if we go back up here, we're going to actually get 3 of these lines because we're doing 3 different values of VSB. And so there will be a second line here and a third line here. They'll all have the same slope because the slope is unrelated to the body effect. It's only related to the transconductance. And so this intercept here, when VSB equal to 0, corresponds to VTO, and you'll get a second VT there and a third VT there. And that's what corresponds to those 3 data points. So where this meets the x-axis, those 3 points, those are what correspond to the 3 points that show up on this graph. VT1, VT2, VT3. If you follow those across to the y-axis. Okay, let's look at the next part of the pre-lab. Part D. Explain how the channel length modulation factors lambda, can be obtained from the plots in part 7. Now, students understand this one quite a bit better. So part 7, the transistors in saturation, and it's always going to be operating, and we're just finely adjusting the VDS value while keeping VGS constant. So if you refer back to your notes or the text, if we plot ID versus VDS for a fixed value of VGS, the curves look something like this. Where in this region might be triode, and in this region we're in saturation. And ideally, once you get into saturation, this becomes a straight line here. That would be the absolute perfect scenario, in which case lambda equals 0. That's not true, especially in modern devices. And so there's a slope component to the current when you're in saturation. As you increase VDS, the current slightly increases. So one way to extract or to parameterize this slope is if we follow this curve back to the x-intercept somewhere over here. This corresponds to a voltage called VA, and lambda is expressed as 1 over VA. So it has units of volts minus 1, because it's 1 over a voltage. So if we get multiple data points here, specifically in this saturation region, we can get a best fit line, y equal to mx plus b, and we can use that to figure out when y equal to 0, you can figure out what the value of x is. And that will correspond to lambda. Well, it corresponds to VA, which is 1 over lambda. So that's how you would figure out lambda from this data. And you can do this for the NMOS and the PMOS. It works the same way. And this goes back into that transistor equation, ID equal to 1/2 K prime W over L VGS minus VT squared. And when you account for channel length modulation, 1 plus lambda VDS minus VDS sat, which is VGS minus VT. Depending on which text you look at, sometimes they leave off this part here, or they modify it slightly. But this is the way that I learned it, and I think it avoids continuity issues at the crossover between triode and saturation. Okay, so the next part of the Prelab is, let's see, preparation for part 2. Calculate the values of VDD that will be required to give the specified VSD values. So let's draw the circuit in part 2. It's a PMOS. PMOS are a little tricky, so students struggle with these. They can be a little confusing sometimes, so I understand the struggle. So source is grounded here, especially with the voltages they have used. It's kind of confusing. This is the diode connected one, so it looks like this. And this is what they call VDD, and you're also going to vary the body voltage too, but I don't think that's important for this question. So for this, they give you values of VSD they want you to use. VSD. Now it's important to realize what this notation means. VSD means the voltage at the source minus the voltage at the drain. Source minus drain, VSD. So they give you this. They want to know how that can correlate to VDD, which is the drain voltage. So VSD, in this schematic, the source is ground, is 0 volts, 0. And the drain is VDD. So just substitute that. You rearrange VDD, drew that a little weird, VDD is equal to minus VSD. So whatever values of VSD they ask you to use, you just take the negative of it, that's what you apply. So for example, VSD equal to 3.5 volts, you would set VDD equal to minus 3.5 volts. Okay, so not as hard as what you might have originally thought when you looked at the question. The next part is pretty similar, but it's for the other PMOS circuit that we're going to build, but it's going to follow the same type of methodology. So let's draw that first. 2.5 volts on the source. We're going to apply a gate voltage that is ground, and we have VDD on the drain here. So again, they give you VSD values again. But remember that that is equal to VS minus VD. So again, that is given. VSD, the source voltage is 2.5 here. Drain voltage is VDD. So VDD is equal to 2.5 minus VSD. And that's the equation you want to use. So for example, when VSD equals 2 volts, which is the first data point, VDD is going to equal 2.5 minus 2, so it's going to be 0.5 volts. When VSD equals, the last point is 5.5 volts, VDD is going to be minus 3. That's all there is to it. And there's data points in between, but you can fill those out pretty quickly. There's no simulation portion to this pre-lab. This is it. So if you were able to follow along and understand that, then you should be good to go for the lab. I know it's kind of a lot, but it's important that you understand the background to this, because if you understand this, then you'll understand the rest of the labs. You'll understand the underlying theory to the rest of the labs a lot better when we get to them.